Professor Ramay, are you there? Could you unmute yourself?
Yes.
Oh, okay, great. So should we begin?
I
Okay.
use a GIF.
Okay.
Good
So
because
welcome back everyone to the second talk of the second session. But today I'm very happy to introduce Professor Oliver Ramay, and he's going to tell us about variations around the Brun-Titchmarsh inequality. Oh.
okay. So hello everyone. It's very sad not to see people, but that's life. I'm very happy to be at this conference. I would of course prefer to be in Chennai, and if all goes well, I'll be there in November. I hope so. We'll be able to have some coffee. Okay. Today I decided to go through a very early result of Balu. 1976, very long time ago, and I decided to show you this result because it's very flexible, and so the method may be used most probably in many different circumstances, and also I'll go slowly. Okay, so what we're looking at is this theorem, which can be extracted from the theorem of Balu and Ramachandra. Take the sum of n primes. P for me, it's a prime. I mean, little p is a prime, capital P is a bound for this prime. And take a parameter gamma. Say gamma is the square root of p, something like that. And look at 1 plus cos gamma log p. That's a non-negative function times log p. And the result of Balu and Ramachandra is that you can give a good size lower bound for this quantity. Of course, you expect this quantity to be of size constant times p, and you don't get the proper constants. 0.0089 is most probably smaller than what it should be, but still it is positive. Okay, if you want to understand a bit what happens, just replace log p by log n, take an integer n, and the derivative of gamma log p or log n is gamma by p. So essentially, the derivative is gamma by capital P. Say gamma is square root P, so it's 1 upon square root capital P. So when n goes from n to n plus 1, your integer, I mean, the quantity gamma log n moves slowly around the circle from n to n plus 1 to n plus 2 and so on. And after p pi gamma n plus 1 plus p pi gamma, you've completed the full turn of the circle, and you don't know exactly where you.
I think you went mute. Professor Ramay, you went mute. Could you please unmute? Sorry, we cannot hear you. Could you please unmute yourself?
Yes.
Yes, now it's better. Now it's better.
I think you muted me.
Oh, sorry. Oh, sorry.
No big deal. At least it gives a feeling of having someone. That's good. So after p goes, I mean, the integer n, let's say, goes in an interval of size p by gamma, you end up on the other side of the circle, and you don't know exactly where you are. So you have to work on this in small interval of size p by gamma. And when you have integers, you can do things. But when you have primes, you may have gaps for these primes. And you don't know exactly where is the next prime. If you have some idea about the distribution of primes, to answer this question, you would need to be able to localize your prime in an interval of size square root p around p. And that's something that we cannot do even on Riemann hypothesis. But still, we can prove that. The second thing that you may say, okay, since analytical means are not going to work, maybe you can use a bilinear form techniques, Vinogradov stuff. But that's not going to work because cos gamma p is essentially exponential I gamma P. So it's I gamma log P. So it's essentially P to the I gamma, and it's multiplicative in P. So bilinear sums are not going to work. Okay, so but I'll show you how easy it is to prove this one. What can we do with that? Here is a theorem that we can prove from it. And then I'm going to use this theorem. So the theorem is that if you take zeta prime upon zeta minus zeta prime upon zeta, for people who don't understand that it's a conference about analytic number theory, I recall that zeta of S is 1 upon n to the s for real part of S strictly larger than 1. So zeta has a simple pole in 1, the residue is 1, and minus zeta prime upon zeta is essentially 1 upon s minus 1, when sigma is close to 1. It can be made into an exact inequality that has been made in a nice manner by Delange in 87, with even some improved inequality. And okay, for the Riemann zeta function, we are very interested in its zeros. And at the beginning, let us have a look at the zeros next to the line real part equal to 1, and even for simplicity, at the line real part of S equal to 1. So assume you have a 0 in 1 plus I gamma. And what you have is that next to this 0, minus zeta prime upon zeta, say in sigma plus I gamma when sigma is close to 1, well, it behaves like minus 1 upon sigma minus 1, plus a constant term. Yes, it's simply the effect of analyticity. It's not minus 1, sorry, because this 0 could have multiplicity. So it's minus m when m is the multiplicity. But let's say it's a simple 0, so it's minus 1. And the theorem I have here, which is a consequence of the previous one, gives me an inequality. It gives me that minus zeta prime upon zeta and sigma, plus a real part of minus zeta prime upon zeta and sigma plus I gamma is larger than something. That's positivity, it's larger than something. If I have a 0 in 1 plus I gamma, the left-hand side is bounded when sigma goes to 1. The right-hand side blows away. And so it means that you cannot have a 0 in I plus I gamma. A multiple 0 would be the same. Even if you want to have a quantification, I mean, not a 0 in 1, but in 0 close to 1, it's easy to see with the factor gamma to the 2 sigma minus 1 that is going to give you a 0-free region of size 1 minus constant upon log gamma. So it's exactly what we want. What is rather amazing with this way of proving the 0-free region is that you don't look at sigma plus 2 I gamma. You just look at what happens in sigma, and in sigma plus I gamma, that's all. Okay, so now I have to prove theorem A, but first I have to prove theorem B from theorem A. And that's very easy, really. I do it for younger people. Minus zeta prime upon zeta, it can be expanded into the Dirichlet series. It's sum of lambda n by n. Lambda n is a von Mankel function. It's a non-negative function. And essentially, it's log p when n is a prime. And then you have the Dirichlet series differs from sum of log p by p to the s by only an analytical and bounded function. But in fact, since lambda of n is non-negative, you can even keep it. So when you look at the quantity we want to consider, which is minus zeta prime upon zeta plus real part of minus zeta prime upon zeta and sigma plus I gamma, well, look at what you get. What happens is that the real part of 1 upon p to the s, or 1 upon p to the sigma plus I gamma, gives you this cos gamma log p. So the coefficient you get on top here is 1 plus cos gamma log p, which is non-negative. The consequence of non-negative is that you can throw away the terms that you don't know how to control. So you can limit your summation for p larger than t squared. And then you use d-adic decomposition. You have a lower bound for this part, and you get the theorem that I stated. So once you have theorem A, getting a 0-free region is real easy. So if I'm not mistaken, I'm going to prove theorem A now. First, I have to say somewhat why it would be difficult. So the first thing I have to do is to recall the prime number theorem in case someone around did not know it. In fact, in this proof, we don't need the prime number theorem. What we need is that a lower bound for the number of primes. We would need that the number of primes less to x, or less to capital P, but less to x, is larger than a constant x upon log x. It's equivalent to say that the number of the sum of log p for p less than x and p of prime is larger than constant times x. But we know that it's equivalent to x. So if we look at the problem, 1 plus gamma log n behaves in interval like size p upon gamma like this bottom stuff. And at the bottom here, you can have some constant times p upon gamma integers. When you sum upon all the interval, you can get a positive proportion of the integers that are close to these bottoms. And of course, the primes are not positive densities and of density 1 upon log p. So maybe they could all be in these bottoms. The information you have is that this bad interval, these bad places are intervals. And that's what we're going to use. To use that, I have to recall the Brun-Titchmarsh inequality, but I'm going too fast. I have to go slower. Well, yes. So the Brun-Titchmarsh inequality, it has two parameters, and I'll tell you about the two of them. So you take a prime in an interval, say between y and y plus x, and you further assume that it is congruent to something in an arithmetic progression. And by using the sieve, Brun was able to prove, I mean, at the beginning, Brun was able to prove, but now everyone is able to prove, that we can give an upper bound for this number. So the upper bound is x upon phi of q divided by log x. That's what you expect to be. You expect this quantity to be x upon phi of q divided by, let's say, log x, for simplicity. And what you lose is this factor 2 on top, you see, which I've put in green. And the denominator is log x by q. In fact, around y, it should be log y, and you have log x by q. So for instance, if you take q equal to 1, which is what I'm going to do soon, and you look at the number of primes in the interval y and y plus y to the 1/3, interval of length y to the 1/3 around y, well, the probability to be a prime around y is 1 upon log y. The interval is of size y to the 1/3. So what you expect, it's y to the 1/3 divided by log y. And what you get with the Brun-Titchmarsh inequality is that it is less than 6 y to the 1/3 upon log y. So you lose a constant, which is really the discovery of Brun. So it is called the Brun-Titchmarsh inequality because of Linik in 1961, if I'm not mistaken. Because Titchmarsh used that in the Titchmarsh divisor problem and used the method of Brun to get it. So Linik decided to call it the Brun-Titchmarsh theorem, and since then it's stuck. Though in fact the theorem that I've stated now is due to Montgomery and Brun. But that's how things are named. Okay, so let us go back to our problem. You see, we have our interval from P to 2P, and we have all this repetition of behavior. So essentially, a proper interval is not exactly a shift of an interval, but it's a multiplicative shift. So you have to look at what happens between P naught, some P and lambda times P, where lambda is essentially, gamma is very large, so exponential 2 pi upon gamma is essentially 2 pi upon gamma. That's a very small number. So you look between p and 1 plus something small times p. And you get this behavior, and you have this bad interval at the bottom here. So I've given some names, p0, p1, p2, pj for the bad points. And you look at some, let's say, multiplicative interval around it, say between beta minus 1 and beta, where beta, put some numerics, is something very small, exponential 0.03 divided by gamma. But it's still of positive proportion. So when p is out of this interval, then gamma log p is out of this collection of intervals. So you see they are centered about odd multiples of pi. So where cos x is equal to -1, and you're aware by a small quantity, which is this one. So when p does not belong to this union of interval, cos gamma log p is strictly larger than -1. You don't save much, but you save something. I mean, you can improve the numeric. Just that I wanted to be clear. Once you have that, now you have to show that all the primes are not in this union of interval. And for that, you have the Brundtland inequality. So look at the length of the interval, get that essentially it's p by gamma times a small constant. And this constant can be as small as you want if you diminish this 0.03, which was the size of the interval. Get the number of primes that you can have at most in this interval with the Brundtland inequality here. Get an idea of the number of interval, multiply all of that, and you get that the total number of primes is essentially p upon log p times something which is a small constant, and this constant can be less than the number of primes. So it means that you have a positive proportion of the primes that are outside of this interval, and that gives you theorem A. So you see, it's a simple consequence of the non-accumulation of primes in interval. What is surprising in this proof is that you don't use integers. Earlier proof of the zero-free region starts from integer. Here, the integer going from the primes to the integer, or from the integer to the primes, is included in the sieve. But for the argument of the zero-free region, you work with primes directly. And that's a very flexible method. Okay, so what can you do? You see the Brundtland inequality, it has two aspects. You have the size, p in an interval, yes, and you have p concurrent to a modulo q. So can you mimic this interval in the q aspect? In fact, in the paper by Ramachandra and Balasubramanian a long time ago, the q aspect was also used, but in a very different manner. Because when you have a new proof of a zero-free region, you wonder whether you can prove that there's no z equals 0, or whether you can improve on the dependence in the parameters. It turns out that they get exactly the same kind of zero-free region that we get usually. Okay, so but we can use the same process in Q aspect in a different manner. So the idea is to say that the primes do not accumulate. What we used in now was that the primes do not accumulate in some interval, and now we want to use the fact that the primes do not accumulate in residue classes, and that's a straightforward application of Brundtland. If you give yourself a modulus q and you look at what happens in z by q z, well, the number of invertible residue classes or reduced residue classes that are covered by the primes less than x, the number of classes is a positive proportion of phi of q. So it's larger than log x by q upon 2 log x. So if you take x equal to q square, you get that the number of primes that are covered, the number of classes that are covered are at least phi of q by 4. And that's absolutely trivial to prove. We have very good explicit bound for the number of primes up to x. And the Brundtland inequality of Montgomery and Boone does the rest. So how can one use this? Well, first, later I'll tell you about how one can use this information. But first, I have to go through another paper of Ramachandra about the factor 2. You know, in the Brundtland you have the upper bound was less than 2x time divided by 5q log x by q. And I want to show you a very simple proof that these two, I mean, if you break this factor 2, then you get a wonderful result. The proof is just in this page, so you see it's very simple. Just assume that for given modulus q and for any class A, reduced class, the number of primes congruent to A modulo q and between x and 2x, that's for simplicity, is less than 2 minus delta for some positive delta, x upon phi of q log x. So I've cheated a bit, it's not log x by q, I put log x. So you need to beat this log x by q and this 2. So you have that. Then if you give, if you take any quadratic character, L1 chi is larger than 1 upon log q. So it's really a very, very strong consequence. And the proof is here. Let me see whether I have, yeah, I have time. So just look at zeta times ls chi, you know, that's not very original, everyone does that. The sum of a of n upon n to the s, and a of n is a real number which is non-negative. For the squares, a of n squared is larger than 1, but that's what is usually used to get a lower bound for L1 chi. So if we use our hypothesis and we look at the quantity sum of chi of p for p between x and 2x, well, chi of p is either 1, either 1 is a minus 1. Let me forget about the prime that divides q. So it's either 1, either minus 1. So this quantity is the total number of primes minus twice the value for the primes when chi of p equals minus 1. And the number of primes for chi of p equals minus 1, you have an upper bound here. So since you need a lower bound and you have a minus, that's exactly what you have. And it gives you phi of q by 2, that's the number of classes A where chi of p is equal to minus 1. Get put your upper bound inside, and what you get is delta minus 1 x upon log x. So instead of minus x upon log x, which would mean that most of the primes have chi of p equal to minus 1, you save a bit of something. You save delta. And then it's rather easy. From this chi of p, you can get to a of n by n. So look at this smooth part. So a of n by n, e n by x minus e n by x. By positivity, you can reduce to the place that you like between x and 2x. Then you can approximate exponential that give you, n by x. So the n disappears and 1 by x appears. an, you can say, I don't know much about an, but I can look at ap. And ap is 1 plus chi of p. And because of the previous inequality, you get that it's larger than delta upon log x. So you have a lower bound for that. Then you use Moline transform. Because of your kernel exponential, you get a gamma factor, which makes things converge extremely fast. And you discover that this quantity, a of n by n, e n upon 2x minus e n x, is essentially L1 chi. Compare this part with the lower bound, get L1 chi larger than 1 upon log. So you see this factor 2 is not to be taken lightly. If you break it, I mean, if you improve on it, you're going to get a wonderful result. So if you want to use the Brundtland, it's better not that you expect to be able to do better than. Okay. What about the factor 2? So that was the factor 2 in the Q aspect. But what can you say about it in the X aspect? There's a talk later by Andrew Granville about some work with Alissa Lumley, and I think that he'll tell you much more than I will on this problem. So is this factor 2 necessary in the X aspect if you forget about the Q aspect? To have an idea of that, you can look at the spacings between the primes. Give yourself an interval between y and y plus x, and look at all the primes you can put inside. So P1, P2, P3, till P kappa. Say. And it's good to look at the spacings. So H2 is between, it's P2 minus P1, H3 is P3 minus P1. So you get P1 plus a set of spacings, H1, H2, H3, H kappa. And these spacings should be spacings of primes, you see. You cannot have P to be a primes, P plus 2 to be a primes, and P plus 4 to be a primes, because one of these three is going to be divided by 3. So you have some conditions on these spacings to be spacings of primes. That's what we call admissible condition. Admissibility is that essentially you do not cover everything. You still have one class where you can escape, just like the primes never cover the class 0. And so the way to look at the factor 2 problem is look at the length of your kappa tuple, which is the space taken by the smallest and the largest. And you want either to get as many primes as you can in this interval, or once you have kappa, the number of primes given, to find the smallest interval that contains them. We don't have much information on that. The basic result on this question is due to Hensley and Richards, and I think Andrew is going to say something better than that. Which we are able to get more than the number of primes. So it means that we have an upper bound which is twice L upon log L, and we are able to find maybe places where you can have L upon log L plus something bigger than that, but it's a little O of L upon log L. And the construction of Hensley and Richards, essentially, you take the primes between minus L by 2 and L by 2. They are of density 1 upon log L by 2, which is strictly larger than 1 upon L. And by playing with this discrepancy between 1 upon L and 1 upon L by 2, they get this improved log 2 here. So that is the only result we have now to improve on kappa. I've read another one, but I forgot, so I'm sorry. Now, numerically, what can you do? Because maybe you can get an idea that numerically it's easy to get an interval where the number of primes in an interval of length L is close to 2L upon log L, or twice pi of L, the total number of primes. There was a website by Engelsmar. This website has disappeared. I don't know when it disappeared, last year or year before, in which he says that he has computed, he has found an admissible tuple of this many number that was covering this length. But I don't have the tuple with me because the website has disappeared and I didn't copy it. So it means that instead of the constant 1, I mean, the number of primes is L upon log L, we can find a place where we have 1.034 primes, if you believe the prime kappa tuple conjecture, of course. But at least it's larger than 1, but you see it's extremely small. I mean, what we're able to prove is 2. I mean, the number of primes in this interval is less than twice pi of L. And what we're able to prove numerically, I mean, to get examples, not to prove, but to get intuition that we can prove, is 1.034. So the problem is, of course, can you improve on that? And what is the real lim sup? Is do we have a limitation of 2 like we have with Ziegler 0? And why? Okay, I stop about this part, and so we are somehow stuck with this factor 2, but we can have a look at large field extension. Let me have a look at the time because I don't see people. Yes. We can do things on average upon the moduli. So this maybe look complicated if you look at it immediately, but essentially what is included here is that take the number of primes congruent to A mod Q, and it should be pi of x divided by phi of Q. So this one is a remainder term. Do the sum upon all the classes and multiply by something, you get that it's less than pi of x by 2. This is valid for Q around a set of pairwise coprime integer. That's only a retelling of the Barbon-Davenport-Halberstam inequality. Sometimes people, I mean, one believes that the large-sieve inequality has to do with sums of characters or with exponential sum. In fact, arithmetically speaking, you have complete sums, which means that you have a complete sum upon A. Okay, A is coprime is Q, but essentially it's, you can think about it like A modulo Q. So it's a complete sum, which means that you count points. And you can convert result from large-sieve inequality to counting points. And that's what this result is. That's how you make this result. And once you do that and you do some optimization process, what you get is that if you give yourself a coprime moduli Qi, and I'm assuming that you are less than x to the 1/4 for simplicity, because I want to state things that you may understand. When you get this inequality, phi of Q upon cardinality of A of Q, I mean, the number of classes that are covered by the primes, -1 is less than 2. So for instance, if you take 3 moduli, Q1, Q2, Q3, for one of them, this quantity is less than 2/3. So it means that for one of them, A of Q is larger than 3/5 phi of Q. And you've beaten the factor 2 with that. Okay, you don't know exactly which Qi you have, but still you can beat the factor 2. That's completely similar to the exceptional modulus behavior. And what can you do with that? Oh, first, yes. Before doing something, I have to give you a crash course on Linux problem. Because maybe you can find a prime in an arithmetic progression that is small. I mean, instead of trying to go through this Bruntic-Schwarz stuff and large-sieve inequality and moduli that you don't control, maybe you can have a look at the simple problem, find a prime congruent to A mod Q, and maybe you can show that you can find a prime less than Q to the 1 plus epsilon. Linux in 44 and has been improved. I mean, Linux in 34 proves that there is a constant L, absolute constant, so that every class's modulo Q, every invertible class's modulo Q, can be covered by a prime less than Q to the L. The fact that it should be not exponential Q, but Q to some power was a major progress. Hillsbrown in 92 lowered the effective value of Q dramatically and reduced it to 5.5. Since then, I don't know of many new ideas that have been introduced on this problem. Xiloris in 2011 pushed the computation of Hillsbrown and published 5.18, you see. And in his PhD memoir, you see 5. But let's say that we can we know that Linux constant can be taken between, let's say, 5 and 5.80. And no one has been able to give a decent value for Q naught. I mean, it is explicit. You can give a value for Q naught, but it's very large up to now. I don't even know of any given value. It's extremely large. If we assume a generalized Riemann hypothesis, so the Riemann hypothesis for all the L functions, we can reduce 5.5 to 2 plus epsilon. And it should be possible to get it explicit. And I think it has been done by Barr and Sorensen 20 years back, but I'm sorry, I forgot. But under GRH, it's possible to get it explicit. Yeah, yes. And most probably, we believe that the good value should be 1 plus epsilon. So, there's some heuristical arguments that tell you that. So there's two issues. Diminish the 5.5 or the 5 of auxiliaries or 5.80 and get an explicit version of it. So that is valid for decent integers Q. Okay. Let me go back. So here we know that out of three, if we have three moduli, one of them has A of Q larger than 3/5 phi of Q. What can you do with that? Well, that's what well, if you give yourself three moduli, coprime, less than x to the 1/4, then for one of them, you can cover all the classes by a product of two primes. It's simply because the primes are very large, and then if you double the size, multiplicative, double the size of the set, you cover everything. There's no difficulty in it. But now there was the problem. We wanted to show that every integer larger than 454 is a sum of 7 non-negative cubes. Linic in 43 proves that every large enough integer is the sum of this many cubes. The proof had been simplified by Watson in 51, greatly simplified by Watson in 55. And then it has been further simplified by McCurley in 84. He made it explicit, essentially by playing with one modulus or two modulus, one modulus or two moduli. The numerical difficulty of this proof is that you need to produce a prime in an arithmetic progression to a very large modulus. For Linic, it was log x to the 9. For Watson, it was log x to the 12, if I remember well. The same for McCurley, it was about log x to the 12. And the prime, the explicit version of the prime number in arithmetic progression that we have are very bad. So what we are able to prove is that every integer larger than 10 to the many, 500,000, is the sum of 7 non-negative cubes. And by removing the primes in arithmetic progression, but putting a product of two primes, and using an identity of Enrico Bombieri, I reduce this enormous bound to 10 to the 230. So you see, we can use this kind of result very with lots of efficiency. And recently, Samir Siksek wrote a beautiful paper in which he finally proves that every integer larger than what we believe is the smallest, larger than 454, is indeed a sum of 7 non-negative cubes. Okay, so that was one usage. What I like about this method is also its flexibility. You know, I started by saying, have a look at the method of Balasubramanian and Ramachandra, and it's so flexible. And in Q aspect, it's flexible also. So for instance, if you look at the primes, so that P plus 1 is the sum of two squares, I mean, say two coprime squares for simplicity, because it seems better. Ivaniak in his PhD proved that you have the good number of such primes. So you have x upon log x to the 3 half. It's a sieve of dimension 3 half for people who understand what I'm saying. But I don't know how explicit, I don't know whether we know we have an idea of this constant here. And you can use the very same method. You can build a similar setting around the Barbon-Davenport-Halberstam inequality, but not with characters, because you don't have any characters anymore in this setting, but you can build the same thing. And what you get is that if you give yourself, if there is an h, so that if you give yourself h coprime moduli less than x to the 1/3, then every class modulo q, I mean modulo one of them, every class modulo q can be covered with a product of 4 of them. I would like to get h, but to get h means that I would like to get a constant in this lower bound here. Even asymptotic, what do we get? And then the proof would unfold, and we would be able to get this explicitly. It's a kind of multiplicative Schnirelmann problem with a complicated sequence. So though we don't know the number of primes, and though this sequence is very complicated, we can prove this kind of result. Okay, but in some problems, you don't want any exceptions in Q. In some problems, you don't want to know that it's out of Q1, Q2, or Q3. You want to know exactly that you can cover the integers with some primes. I mean, the classes modulo Q with some primes. So I was giving some talk about what I done on sums of 7 cubes, and what were the limitations of product of 2 primes. And Aled Walker was very young at the time, and he was in the room, and he said, "Well, you know, I can do something so that we can push a problem not for 2 primes. We don't want P1, P2 to be to cover everyone, but P1, P2, P3." And then we started working with Aled, then with Oriol Serra and Priyambad, and now I'm trying to get my Balu number down to 1, because just now my Balu number is 2. So I would like to write a paper with Balasubramanian, and it's in progress. The paper is written. It has to be published for the Balu number to be officially equal to 1. But I hope that by the end of this year, I'll be able to say that I'm a 1 Balu person. Okay, so what we have in our bags just now is this theorem. Take a modulus Q larger than 10 to the 30 when we are working hard on the numeric, but the proof is difficult. We can find 3 primes, P1, P2, P3, less than Q to the 5 half, so that P1, P2, P3 is congruent to any class you want. I mean, give yourself a class, you can find P1, P2, P3, so that P1, P2, P3 congruent to this class modulo Q. What we had with Aled was something larger than 5 as an exponent. What we had with Priyambad and Oriol was 3. So this one is published. And what we're able to get now is less than 3, 5.5. The earlier method was blocked at 3, so we are rather happy with this one. So you see, now we have no exceptions in Q, but we've lost 1 prime. We have 3 of them. But still, we have exactly 3 of them. It's P1, P2, P3, not a P3 primes, not an integer that has at most 3 prime factors. We have exactly 3 prime factors. And we are rather happy about that. It's still explicit. We have some difficulties, but it's still explicit. And of course, we wanted to go beyond the exponent 2, because on Riemann hypothesis, in general Riemann hypothesis, we have 2 for primes. And that we've been able to get, in fact, by the same method. The proof is much simpler, in fact. So we can prove that given q and given epsilon, and given a place r a prime to q, we can find three primes p1, p2, p3 less than q to the 3/2 to the epsilon, so that p1, p2, p3 is congruent to a mod q. And we were very happy because the 3/2 is less than 2. Okay. Okay, after that, we have difficulties that I don't want to. I've given several talks on this problem, so I don't want to enter this part. There's a recent paper by Petrov and Yang. I mean, a preprint, but I guess that it will become a paper soon. If Q is cube free, we can reduce, I mean, we can use their result and reduce 3/2 to 4/3, which is getting closer and closer to 1. And I mean, we have some other condition. I mean, if you assume that all the prime factors that divides Q are congruent to 3 mod 4, we can get 11 by 8. You see, it's we're getting close, but additional difficulties are showing their nose. So let me go slowly, no, not slowly, but fast around some elements of proof and to go. So we need some additive combinatoric, and that will be given by Knesser's theorem. But it's not in my talk now. What we'll need is a brilliant idea of Priyamvad, a student of Balu, to prove a Brundtland inequality for cosets. I like this inequality quite a lot, so let us state it. Give yourself a subgroup of index y of z by q z star. Yes, I should have put the multiplicative subgroup here. So H is a multiplicative subgroup. And assume the index is very small. I mean, index 4, 5, 6. It can go till a rather large value, but in fact, assume that the index is very small. So you have a very large subgroup. Yes. And look at the number of primes in the coset of this subgroup. Then you can improve on the large sieve on the Brundtland inequality, not on the factor 2, because that you cannot. But instead of having x by q, you can have x by square root of q. You lose y, but y is going to be a constant. What is rather amazing also with this result is that it is valid even if x is less than q. X can go till the square root of q, in fact. And that's what we've used in the result. So it's one version of, I said, variations around the Brundtland inequality. One variation is this one, valid for very low values of x with respect to q. Okay, this one forget, excuse me. No, not forget. The theorem we have with Balu and Priyamvad, we will have to take care of three problems. So the first one is what I'm going to talk about. We have to get a large density, which is given by some Brundtland inequalities. And then we have to go from the density to the individual representation. So it's Knesser's theorem and anything additional you can find. And we've added some P2 numbers. And then because of Knesser's theorem, we have difficulties of accumulation of primes in subgroup. And that we have to handle. So that was what Aled Walker brought at the beginning in what I was doing. He said that if you use some lower bound for L1 chi, you can avoid the accumulation in a quadratic subgroup. And then we added some other stuff to avoid accumulation in more subgroup. So let me conclude this talk with a vertical Brundtland inequality. Something that so what do we need in this problem? That we don't need exactly to know that for one class the primes do not accumulate in this class, but we want to show that the number of classes where the primes accumulate are small. That's what we want, and what we prove is in fact It has been already proved by Roulet in 72. But what we've introduced in the proof, let's say, we are able to get x upon square root of q instead of x by q. For almost all a, that's what this inequality tells you here, it's almost all. And for x as small as q to the 3/2, what we have is that the proof is simpler than the earlier ones. So we can make it completely explicit and with rather decent constant. Also, the phrase, I prefer this phrasing here because you see immediately where you can what are the constants you have to compute, really. When you say for almost all classes modulo q, it's a bit vague. So that's what finally calls the vertical Brundtland inequality. That with analogy of Sato-Tate distribution. So the horizontal counterpart has been studied quite a lot. I mean, you fix A and you vary Q. Here we have Q fixed and we vary A. We have less material at our disposal because we have only the multiplicative properties modulo Q and we know it not so well. I'm just going to show you very fast how one proves this one, and then that will be the end. Essentially, because I'm going to have a look at the smooth version. So you put eta, which is a smoothing function, so that things are going to go better way. You take a sieve weight here, which is almost Selberg's sieve here, which is uniform with respect to the class, like an enveloping sieve. Just develop everything, blah, blah, blah. And lambda d1, d1 and d2 are supposed to be small. That's the idea of the sieve. d1, d2 is small. So you put them in front and you see what you have inside. And what you have inside, well, you have the trivial character. Yeah, for the inequality, we have a trick with Robert Rumley from long ago, which makes that you can reduce to primitive characters. That's going to simplify your life. Anyway, for chi equal, so chi naught, chi equal 1, in fact, you have the main contribution, which is this one. And for chi not equal to chi naught, you convert it into, you express it in terms of Boolean transform. Okay, that's the big expression you have here. And now you have to handle this integral, where k is the one with the Selberg coefficient here. And of course, here you have to wonder what you're going to do. I mean, whether you want to exploit the bilinear structure of k, I mean, almost bilinear structure of k, whether you want to exploit the force power moment. And in fact, what we do is extremely simple. We take the L infinite norm. I mean, we push the line of integration, of course. But we take the L infinite norms out for LS chi, and we use hybrid Lyapunov inequality for this polynomial, which is already square. So it's, of course, you need some explicit version of all of that, and you need some simplification of Selberg weights and let's say more theoretical viewpoint. It's at this level here where we simply take the L infinite norm out, and we have a hybrid Lyapunov inequality, which is simple enough. I'm going to end the talk here because I went through enough material and it's time. Thank you. Over.
Thank you, Professor Ramay, for this beautiful talk and very interesting results. So let me open the room for questions. If you have any questions, please unmute yourself and ask.
Oh, hello. I just have a quick comment about the Hensley-Richards result that you mentioned earlier. The secondary term has been improved recently by Konyagan by a log-log factor. I haven't seen the the actual paper, but he spoke about it in one of these online seminars.
Oh, beautiful. Thank you.
Yeah, it was the number theory web seminar sometime last fall. So
Yeah,
I think those are available online. Yeah.
Thank you. I
I have a question about something you said at the very beginning. If you could maybe scroll back.
yes.
Yeah, I think this is just a terminological question, maybe. Yeah.
Where?
I'll tell you when to. Okay. Yeah, there. So you said that this theorem, you get nothing by analytic means, even on RH. So if you just look at the sum of p to the I gamma and write it as a prong integral and move the line of integration into certainly on RH to the 1/2 line or into a classical zero free region for zeta, don't you get something like this?
I don't think so. With the classical zero free region?
Yeah.
If you tell me that I should look at it, it's a long time I haven't looked at that. I don't think so. But
so, I mean, you said that a way of approaching it would be to split the primes into intervals of length, something like square root p, if gamma squared is p, let's say, and try to understand the number of primes there. And that certainly you couldn't do, even assuming RH, if you fixed an interval of length square root p. But
you using the collection of intervals from the very beginning.
Yes, exactly. So you don't just have a single interval here, you have a lot of intervals covering p to
yes.
p.
I have to. I cannot do it online. I have to think about it.
Yeah, okay. I mean, I think this does follow from, certainly from RH, and I think from the classical zero free region, but not if you try to split it up into little intervals, it won't work.
Yes.
If you just keep the sum complete from the start.
I have to have a look at it. Sorry.
Okay.
Yeah, thanks.
Any other comments or questions? Okay, if not, let's thank the speaker again.
Thank you.
So we will resume the next talk in about 2 minutes. Okay, so Adam, could you please share your screen and get it all set up?
Yes, I will do that. Can you see my slides?
Yes, I can. Oops, perfect. So we still have a couple of minutes.
Okay.
Adam, could you make it full screen?
Yeah.
Okay, great. Thanks.
Hello, sir. You asked some question to Ramay. No, I didn't understand the question. What is it you wanted?
So the question I asked was, so you have this bound for the sum of 1 plus cos gamma log p.
Correct.
For which you proved a lower bound using the sieve, which is very nice.
Uh-huh.
And he said that there was no analytic way to approach this, even assuming the ring hypothesis.
Yeah.
And this is the thing I was saying, I didn't think that was right.
Okay, let's put this way. Suppose you already assume certain zero-free region.
Yes.
Okay, then it is trivial.
Yes.
What we are trying, but for the zero-free region, normally you also assume something on 1 plus 280.
Yes.
We wanted to say ab initio without starting in knowing anything about 1 plus 280.
Yes.
Whether you can get a zero-free region.
Yes, I understand. I was just commenting that saying that analytic methods can't do it seems a bit misleading, because there's a kind of, as you said, there's a straightforward analytic way to do it if you assume certain things. If you don't want to assume those things, then it's not straightforward.
No, you see, for example, there was a comment by Ingham that this method will give a zero-free region, but it will not give a lower bound. And we just wanted to show that this method of this Ramanujan's identity will actually give you a lower bound, not only the zero-free region, but lower bound without involving anything on 1 plus 280.
Yeah, that's fine. I agree with that.
Yeah. Okay, that's a point. But on the other hand, if you assume zero-free region, there is nothing to prove.
Yes.
Just Perron's formula would give it immediately.
Yes, but I mean, I think that a zero-free region is an analytic piece of information, right? So if you're saying that there's no analytic approach, a zero-free region is an analytic approach.
Okay, so it's time. So I'm very happy to introduce our final speaker of this session, Professor Adam Harper from University of Warwick, and he's going to tell us about large fluctuations of random multiplicative functions. Over to you, Adam.
Great, thank you very much. And thank you to the organizers for inviting me to speak here. I'm very pleased to be able to do it, and to have just had a little bit of nice mathematical discussion, even remotely. So some people have seen me give this talk before. I apologize to them. It will probably be very boring, but I hope that for people who haven't heard this talk before, it won't be so boring. So the plan is that first there'll be an introduction. I'll tell you what random multiplicative functions are and some of the things we know about them. And I'll state a new result. And then I'll say something about the proof. Depending on how the time goes, I might say more or less about that. But I'll give some idea of some of the ideas involved. And then at the end of the talk, I'll make a couple of remarks. Most of the talk has quite a probabilistic flavor. So if you don't like that, if you wait to the end, there are some things that aren't probabilistic at the end. So to motivate this, I want to talk about the Mobius function a bit, which is something that many people will be familiar with, but maybe not everybody so much. So what is the Mobius function? It's a function defined on natural numbers. And you define it to be 0 if the natural number has any repeated prime factors. And if n doesn't have any repeated prime factors, then it's just 1 or minus 1, depending on the parity of the number of prime factors of that. So for example, mu of 1 and mu of 6 are both 1 because 1 has 0 prime factors and 6 has 2 prime factors, and they're all distinct. And mu of 2 and so on is minus 1, mu of any prime is minus 1. And mu of 4 is 0 because 4 has a non-trivial square factor. It's divisible by 2 squared. And the kind of major property of the Mobius function is that it's multiplicative, by which I mean that mu of n times m is equal to mu of n times mu of m, provided n and m are coprime. And you can see this just from the definition, because if n and m are coprime, then when you take n and m, you just concatenate the prime factorizations of n and of m. So the condition of not having any repeated prime factors just splits up as a separate condition on the prime factors of n and of m. And the total number of prime factors, where you just add up the total number of prime factors of n and of m to get the number of prime factors of n and m. So the parity thing works out. So this is a nice kind of multiplicative function that takes the values 1 and minus 1 and 0 sometimes. And it's really interesting. It's very highly studied. And the reason for that is because it's closely connected to the Riemann-Zeta function and through the Riemann-Zeta function to the distribution of primes. And I want to say why, people haven't seen this before. So if you give yourself some complex number S with real part strictly bigger than 1, you can form the Dirichlet series whose coefficients are mu. And this converges absolutely when the real part of S is strictly bigger than 1. And you can multiply this by the Riemann-Zeta function. And if the real part of S is strictly bigger than 1, the Riemann-Zeta function is given by an Euler product, the product of the primes, this. And you can show that the Dirichlet series with coefficients mu is also given by an Euler product. It's given by this product of a primes. And at least if you don't worry about convergence, this is easy to check, because if you expand out the product over primes, what do you get? Well, you can get product of any powers of primes that you want in the denominator here, these p to the s factors. But you can only get one copy of every prime, because I only have 1 over p to the s in every bracket here. So I can only get square-free numbers n in the denominator here. I can't get p squared factors, for example. And the coefficient I get is I get -1 multiplied together once for every prime factor of the number. And that's exactly mu of n. So this is the Riemann-Zeta function, this Euler product. This Euler product is this Dirichlet series of coefficients mu. And the point is that the factors here exactly cancel with the factors here. So this whole thing is just 1. And what that means is if you're interested in small values or zeros of the Riemann-Zeta function, so the Zeta function doesn't actually have any zeros with real part bigger than 1, but let's say small values, then because of this identity, because zeta times this other Dirichlet series has to equal 1, if zeta is getting really small, then this Dirichlet series with coefficients mu must be getting very large. So small values or sort of zeros of zeta correspond to large values or poles of this Dirichlet series. Now, understanding when they occur is equivalent to understanding the partial sums of the Mobius function. So this is a reason that the Mobius function is really interesting. I'll say some more about it in a little while. Now, in the 40s, Winkner wanted to try to understand how the Mobius function might behave. And to do this, he wanted to introduce a random model for the Mobius function, which would copy some of its important properties. And in particular, he wanted to copy the multiplicativity property that the Mobius function has. So this property here. And this thing that he introduced to do this is now called a Radimaca random multiplicative function. So this is the main topic of this talk. So I want to try to explain how this construction works. Coin tosses. These are called Radimaca random variables, these kind of +or -1 random variables sometimes. And these gave the values of his function that he was constructing on the primes. So the value f of p for p prime was just this sequence of independent +or -1 random variables. And then he wanted to extend this to a function on all the natural numbers. And he did that by saying that f of n should be 0 if n is not square free. And if n is square free, then f of n should just be the product of f of p for all the primes p that divide n. So this defines this random object on all natural numbers. And if you look at some of the properties, this is indeed multiplicative. So f of nm is equal to f of n times f of n whenever n and m are co-prime, just like for the Mobius function. And the reason this holds is just like for the Mobius function. So if n and m are co-prime, then to get the prime factorization of nm, you just concatenate together the prime factorizations of n and of m, and they don't interact. So the square freeness condition just splits up as a separate square freeness condition on n and on m. And if they are square free, well, f of nm is just the product for the primes dividing n times the product for the primes dividing m, which are all different primes. And that's f of n, f of n. And just by construction, f of n is equal to 0, like the Mobius function, if n has non-trivial square factors. And if n is square free, so if it doesn't have any non-trivial square factors, then f of n takes the values +or -1, depending on the values of these underlying f of p, and so does mu. So f looks maybe a bit like the Mobius function. It takes the same set of values, although it takes them in different places, and it has this multiplicative. And so Winkner's idea was to study this random object to try to give maybe some insight into how the Mobius function itself was behaving. Now, there is another kind of random multiplicative function, which I'll briefly mention. For the purpose of this talk, you can just think about this Radimaca case, if you like, this definition 1. But this second kind of random multiplicative function is actually more useful these days, I would say, and will be relevant to the thing I'll say at the very end. So these are called Steinhaus random multiplicative functions. And the way you get them is now on the primes, you define your function to be an independent sequence of random variables, but now uniform on the unit circle instead of plus or minus 1. So uniform on the complex numbers with absolute value 1. And to make this into a function on all the natural numbers, you now don't worry about any square freeness condition anymore. You just say that for all natural numbers, f of n should be the product of f of p to the power a, where p to the a is the highest power of p that divides n. So whatever the prime factorization of n is, you define f of n to be the product of copies of f of p's corresponding to the prime factorization. And this gives you a random complex valued multiplicative function. It has this property. So f of mn is equal to f of n, now for all m and n. Actually, because of the way this is defined, you don't need any coprimality condition. And whereas the Radimaca random multiplicative functions were supposed maybe to be modeling the Mobius function, these Steinhaus random multiplicative functions, they're supposed to model complex Dirichlet characters, so non-real Dirichlet characters, or functions like this, functions like n to the minus it for fixed real. And the key thing to note here, if you've maybe got a bit lost with some of the details of the definition, is that these values f of n are not all independent of one another. So some of them are, so on the primes, they're independent because that's how they've been constructed. But if you look at the sequence of f of n for all the natural numbers, they're definitely not. So for example, f of 6 is just equal to f of 2 times f of 3 by definition. So if we know f of 2 and we know f of 3, we exactly know f of 6. So this sequence of random variables f of n, they're not all independent. And that means that kind of classical probabilistic techniques will not tell us very much about the behavior of f of n, at least applied in the kind of standard way. So maybe this would be a good point to ask, are there any questions about what I've said up to here? If anything's not clear, please ask. Okay. Right. So I said earlier that there was a kind of connection between the behavior of partial sums of the Mobius function and small values or zeros of the Riemann zeta function. And this is part of the connection. So it's conjectured that the partial sums of mu of n up to x. So this sum in principle could have size about x because it's a sum of things that usually have absolute value 1, and it's a sum of about x of them. But it's conjectured that this should be much more than that. There should be a lot of cancellation between the plus and minus 1 signs. So it's conjectured that this sum should be of size big O x to the half plus epsilon for any fixed positive epsilon. And the truth of this conjecture is equivalent to the Riemann processes. So proving good bounds for partial sums of mu is very interesting and presumably also very difficult because of this connection. And what Winkner wanted to do was to look at his random model, so take his Radimaca random multiplicative functions and sum them up, and think about how this behaves, and see if that will give me any insight into what might be happening for mu. And since this is a random sum, we have to think about what kind of bounds we might get. And what Winkner specifically wanted was bounds that hold with probability 1, which are called almost sure bounds. So we wanted to know with probability 1, how big would these sums be? And the thing he had in mind, and that he mentions specifically in his paper, is this very nice classical probabilistic result, the law of the iterated logarithm. So what this says is that if you take a sequence of independent plus or minus 1 coin tosses with probability half each, but now completely independent, so there's no multiplicative structure here, it's just an independent random sequence, then almost surely the partial sums of this, the lim sup of these partial sums divided by square root 2x log x is 1. And also almost surely, so with probability 1, the lim inf, the same thing is minus 1. So with probability 1, the partial sums get out as big as square root 2x log x sometimes, so along some infinite sequence of x. And they get as small as negative square root 2x log x along some infinite sequence of x. And they don't get more positive or more negative than that, almost surely. And something just to note here is that if you just fix an x, look at the behavior of this partial sum, well, this is a sum of a lot of independent random variables. So by the central limit theorem, this should be behaving like a Gaussian with mean 0, because they all have mean 0 and variance about x. And the Gaussian random variable with mean 0 and variance x usually has size like a square root x, like its standard deviation. And here we're renormalizing by something which is bigger than that, something which is like root x log x. So this law of the iterated logarithm, this theorem, it says that when you look at all the values of x taken together, you get sort of bigger fluctuations than you would expect. You just situate yourself at a single point. So this result doesn't just say something about the distribution of the sum of individual x, it says something about how they all piece together. So it's quite an interesting and deep result for that. And what Wigner wanted, ideally, was some kind of statement like this, but for his random multiplicative object, which has a number theoretic structure. So I want to go through quickly some of what was proved about this partial sum of a random multiplicative function. So Wigner himself proved that partial sum is big O of x to the half plus epsilon, almost surely for all epsilon. And it's almost surely not big O of x to the half minus epsilon. So with probability 1, it doesn't get bigger than x to the half plus epsilon, and it does get bigger than x to the half minus epsilon along some infinite sequence. And this big O bound here, if we could prove this for the Mobius function, remember this would prove the Riemann hypothesis. So he proved that almost surely sums of these random multiplicative functions satisfy the equivalent of the Riemann hypothesis. And then this was improved in some unpublished work, Burdish. So he proved that the partial sums are big O of root x times some power of log, and they're not big O of root x divided by some power of log, almost surely. And this was improved again in a very nice paper of Hollash in the 80s. So this is a bit difficult maybe to pass if you haven't seen this before, but basically, so root x times a power of log is root x times e to some constant times log x. You write log to the power ax as e to the a log x. And what Hollash proved essentially is that instead of having e to the a log x, you could have e to the a square root log x in the upper bound. And similarly, you could have e to the minus some constant square root log x in the lower bound. So we put a square root into the exponents. And there are lots of nice ideas in this paper, which, for the sake of time, I don't think I'll get into trying to describe them all now. But this is well worth a read. And then most recently, the upper bound was improved by Pascal and by Lao, Wu. So they proved that almost surely these partial sums are big O of root x times about log x squared. Root x times log x to the 2 plus epsilon, only fixed epsilon. And I improved the lower bound. So I proved that almost surely the sums are not big O of root x divided by power of log, divided by log x to about the power 5 over 3. And something I would say, I don't want to get into the details of what Hollash did here, but these later papers here are sort of building on the basic method of Hollash. So what I did uses the same kind of strategy for getting lower bounds that Hollash used, but introduces some tools from Gaussian processors to make it more efficient. And similarly, what Pascal and Lao and Wu do to improve the upper bound follows the same kind of basic strategy as Hollash, but with a kind of clever splitting device, which makes the moment bounds that he uses work much better. But all the kind of strategy of these arguments, the underlying strategy, goes back to this Hollash paper. Now, in this talk, I want to concentrate on the lower bounds. So let's just look at the lower bounds that I've written here, and note that all of these lower bounds are functions which are smaller, which are slower growing than square root x. So this is square root x divided by a small power divided by x to the epsilon. This is square root x divided by power of log. This is square root x divided by power of log. So all of these bounds here are consistent with the fact that the partial sums of the random multiplicative function could always, almost surely, grow slower than square root x. And that's a very strange situation, which we wouldn't usually expect to see. But there's no reason a priori that that couldn't happen. Let me just say as well, I don't know if somebody's asking a question in the chat. If they are, I can't see it. But if you have a question, please just unmute yourself and shout, and I'll try and answer. So Hollash asked us a question, is it true that the partial sums of the random multiplicative function should be big O root x almost surely? So is it true that actually the growth is only as big as square root x, the fluctuations only as large as square root x almost surely? And he happened to ask this in the Steinhaus case, but I don't think there's any reason we'd expect the answer to be different if you look at the Radimaca case. And on the other hand, Erdős conjectured in the Radimaca case, but again, I don't think we'd expect there to be a difference, that this shouldn't be true. So he conjectured that the partial sum should not be bigger over root x, almost sure. And he also said in this paper where he made this conjecture that so far as he knew, nobody had a plausible guess for the real almost sure signs. So nobody had a guess for what would be the real analog of the full reiterated logarithm in this random multiplicative. Okay, so the result I want to say something about today addresses these things. So it answers this question of Hollash, and it proves this conjecture. So this is the theorem. So if f of n is either of the kinds of random multiplicative function that I've been talking about, but you can just think of the Radimaca, the real case. And v of x is any function that tends to infinity, however slowly. Then almost surely, so with probability 1, there'll be arbitrarily large x, for which the partial sums are bigger than root x times log x to the 1/4 divided by v of x. So in particular, you could take v of x here to be something like log x to the power 1/100, say. And then the thing on the right-hand side would be root x times a positive power of log of x. So it'd be something that grows appreciably faster than root. So this shows that the sums are not bigger over root x almost surely, they get bigger than that. And as I'll explain at the end, I still think it's true to say that nobody has a plausible guess for the kind of real order of magnitude, so up to constants of this sum, at least I don't. But I think it's plausible that this exponent 1/4 is the correct exponent in this problem. And at the end, I'll say why. So what I want to do next is try to explain how the classical log iterated logarithm, so this statement here, just for completely independent random variables, is proved, or a way of proving it. And then once I've done that, I want to try to explain how you can adapt that strategy to the random multiplicative case. But before I do that, are there any questions about the statement of the theorem, or any other questions up to this point?
So does that indicate that for the Mobius function, this log x to 1/4 should be the truth?
I would say not.
Okay.
So I think for the Mobius function, there's an alternative conjecture based on a random theory, which would be root x log x to the 5/4. That's right. And,
oh yeah. I remember now. Yes.
Yeah, and in my view, that's much more plausible for Mobius. But what I'll say at the end is that this probably does suggest what should happen for partial sum characteristics. I think it's a good model for that case. It's not actually a good model for the Mobius function.
Also, can you remind me the two kinds of random multiplicative functions?
Yeah. So the Steinhaus one is the one that takes values on the unit circle. So it's supposed to be modeling complex Dirichlet characters.
I see. The other one is plus minus one.
Yes.
Okay. Thank you.
Okay. Any other questions or comments? Okay. If not, so let me try and talk about the lower bound part of the classical Fourier algorithm. So by that I mean proving that there are large fluctuations, the partial sum of the sequence of independent random variables. The way I'm going to do this is certainly not kind of novel to people who think about this a lot, but it's probably not the way you'll have seen this proof done if you've seen a kind of first course probability that handles the logarithmic. And I'm presenting it this way because this will generalize better to the random multiplicative case. So I claim that it will suffice to prove that if you take your partial sums of your independent signs and you rescale them in the natural way, like standard deviation, and you take the maximum over some interval, let's say between capital X to the 8/7 and capital X to the 4/3, but it doesn't really matter, just some fairly big interval. It will suffice to prove that the maximum of this is bigger than about √2 log x, with probability tending to 1 as capital X is here, tends to infinity. And why will that suffice? Well, if the maximum is bigger than this, with probability tending to 1, that means the complementary thing, the maximum being smaller than this, will happen with probability below 1, so probability tending to 0. And if that's true, then we can find a sparse sequence of values capital X, depending on how quickly this little o1 goes to 0, so that along that sparse sequence of capital X, these failure probabilities are like, let's say, 1 over the squares, like the reciprocal of the squares. And then if we sum up those failure probabilities along that sparse sequence of capital X, it will converge, because the sum of 1 over the squares converges. And then there's a nice and actually very easy to prove result from probability theory called the first Cantelli lemma. And that tells you that if you have a sequence of events and the sums of all their probabilities converge, then with probability 1, only finitely many of those events will occur. And remember that these events we're talking about here are the failure events, the complement of this. So the first Cantelli lemma will tell us that almost surely only finitely many of these failure events will occur along this sparse sequence of X values. And that's another way of saying that from some point onwards along this sparse sequence of capital X values, this will always hold its success event. And the difference between this way of talking about the proof, this is just kind of the start of the proof, but the difference between this structure of the proof and what you might have seen before is that here I'm using the first Cantelli lemma, and often you would use the second Cantelli lemma for this existence of large fluctuations part. But the second Cantelli lemma requires that the events that you're working with are independent. And that's a big problem for random multiplicative functions. We'll never be able to engineer things for random multiplicative functions so that our events are exactly independent. Whereas the first Cantelli lemma doesn't require any independence assumptions. It just requires that the sum of the probabilities of the events converges. But the price you pay for that is that to get the sums of these probabilities to converge, you need to know this lower bound occurs with probability tending to 1. If you're able to use the second Cantelli lemma, you just need these probabilities to be not too small. I won't get into that, but if you've seen a proof of this using the second Cantelli lemma, you'll understand what I mean. So what we've done here is to move some of the kind of difficulty about. So you don't need to know independence of these events anymore, but you do need to know that they occur with probability tending to 1. So what I want to explain is how you can prove that happens, how you can prove this does hold with probability tending to 1. So if you just fix an x, this rescaled sum by the central limit theorem has a roughly Gaussian distribution, a roughly normal naught 1 distribution. And we know everything about a single Gaussian variable. But what we have here is the maximum of a bunch of these random variables corresponding to different little x. So we need to understand the relationship between these sums as little x as the endpoint variance. We need to understand the dependence between these sums. And the great thing about Gaussian random variables, which is a thing I always try to emphasize in these probabilistic number theory talks, and if you don't take anything else away, I hope you'll take this away from what I'm saying, is that the Gaussian random variables, to understand the dependence structure, you only need to understand the means and the variances and the covariances. And that's absolutely not true for general kinds of random variables. But for Gaussians, for jointly Gaussian random variables, that's all the information you require, in principle at least. So here we understand the means and the variances. These have mean 0 and they have variance 1. So to understand the dependence, we need to understand the covariance or the correlations. And that means the expectation of the product of this sum for different x and y. And actually, it's pretty easy to see what this will be. So there's a factor square root x and square root y that comes out here. And then when you take the expectation of the product of the two sums, because the epsilon n's are independent of one another, the only terms that survive are the ones that occur in both sums. So that's the ones that go up to the minimum of x and y. So this covariance will be the minimum of x and y divided by square root xy. And you can see that that's at most 1. Which is good. It's a kind of sanity check because it has to be at most as big as the variance, which is 1 from up here. And if you decide just to look at points of the special form of powers of lambda, for some fixed lambda bigger than 1, let's say, so look at some kind of geometric sequence points. Well then, so if x and y are of this form and they're not the same point, then whichever one of them is bigger must be at least lambda times as big as the smaller one. I have two different points in the sequence. So that means that the thing in the denominator here, so the bigger one of these will be at least lambda times as big as the smaller one. So that means the denominator here will be at least square root lambda times as big as the numerator. So along this sequence, for all different points x, y, we're getting upper bound for this covariance, which is like 1 over square root lambda. So if lambda is large, this is getting small, and that's sort of getting closer to the situation of these things being independent. So kind of the smaller the covariances, the more independent the random variables, the random sums are. Now we're interested in the maximum here over this interval. So how many of these kinds of points can we actually fit into this interval? Well, it's log of this end point divided by log lambda minus log of this other end point divided by lambda, essentially. And that's some constant times log x over log lambda. Okay, so if you look at just values of x of this form, we can have about this many of them in this interval, and we have this, this kind of understanding of their covariance structure. And then, as I said, for Gaussian random variables, if we know their covariances, we know an awful lot about how they behave. So for example, if I have some standard normal random variables, so some Gaussian mean 0 variance 1 random variables, and I know that all their correlations for I not equal to j are bounded above by rho, where rho is some fixed thing strictly less than 1, then you can prove that the maximum of these Gaussians will be bigger than about square root 2 1 minus rho log n, with probability tending to 1 as the number of random variables tends to. So if rho was 0 here, so the correlations were at most 0, that would essentially correspond to the GI being independent of one another. And then it's quite a well-known fact that the maximum of n independent standard Gaussians has size like square root 2 log n with very high probability. And this is a generalization of that, the case where these aren't independent, you just have this kind of control on their correlations. So if we look back at the setup here, so the upper bound we had for the covariances was 1 over root lambda. So we could take rho to be 1 over root lambda. And the number of tries we had, the number of Gaussians, was this thing here. And if you plug all that in, where you get square root 2, you get 1 minus rho is 1 minus 1 over root lambda. And log of this, well, it's basically log x. There's a small amount of dependence on lambda from the denominator here, but I've just kind of put that in the below 1 here. A lambda here could be anything. So if we take lambda arbitrarily large, we can make this as close as we want to square root 2 log x. which is what we're trying to prove. So this is a proof of the lower bound part, the existence of large fluctuations for the classical law of iterative logarithm. And let me say that what I've shown you here is basically a real proof. So I didn't actually show you the proof of this fact, but it's not too difficult. Now, I didn't actually show you a proper statement of the central limit theorem that would suffice to treat all these things as Gaussians, but that also can certainly be done. And everything else I showed you here is correct. So there aren't any really lies in this proof. And the key thing that made this work was that for Gaussians, we just need to understand the covariance structure to understand, for example, how large the maximum will be, and we could compute the covariances. So can we do something like this for random multiplicative functions? So this is going away from the strategy that Hollash introduced in his paper, which I haven't actually explained to you how it worked, and going back to something more like the classical probabilistic approach, proving the existence of large fluctuations. So can we do this for random multiplicative functions? Well, of course, the answer is yes, because otherwise I wouldn't just spend that time telling you about it. But there are some significant issues. The biggest one is that if you look at the partial sums of the random multiplicative function and you rescale in the obvious way, by the standard deviation, this does not have a roughly Gaussian distribution. Remember before, when we were just looking at sums of completely independent things, this was roughly Gaussian. It's not in the random multiplicative case. That's not obvious, but it's true. And in fact, if you rescale in this way by square root x, this thing will usually have size like 1 over log of x to the 1/4. That's something I proved a few years ago, but it was published last year. So if you rescale in this way, this thing will actually be tending to 0 in probability. It will have size that's usually quite small. And even if you change the rescaling here to take account of this, this still won't have a roughly Gaussian distribution. And everything I said about just needing to understand the covariance structure to understand the maximum was for Gaussian random variables. So this is a real issue, but we can get around it. I want to try to explain how. So I think I'll talk about this for maybe 5 to 10 minutes, and then I'll give my 2 closing remarks, and then I'll finish. So as before, it will suffice, I claim, to prove theorem 1, the lower bound for the sums of a random multiplicative function, to show that if you look at the maximum of these partial sums, we scaled root x over some big interval, let's say between capital X to the 8/7 and capital X to the 4/3. This will be bigger than log x to the 1/4 over v of x, with probability tending to 1. So we don't have root 2 log x here anymore. We have the thing that we're shooting for in theorem 1, log x to the 1/4 divided by this function v that's tending to infinity. But apart from that, this is exactly the same as the start of the proof that I showed you for the law of iterative logarithm. And the reason this suffices is exactly the same as in that case by the first well-contained lemma. And I claim that actually it will suffice to prove something like this, not for the complete sum here, but just for the sum over numbers with a fairly big prime factor. So the sum over numbers with a prime factor bigger than capital X, where capital X is the parameter. And also you can take the real part here if you want. So if you're thinking of f as a Radimaca random multiplicative function, it's real valued anyway, so this is redundant. But in the Steinhaus case, it's a bit convenient here to take the real part rather than working with the whole complex value itself. So why does it suffice to do this? Well, certainly if you can show the existence of a large real part, then you have the existence of a large absolute value. Why does it suffice to work with just this subsum over the numbers with a big prime factor? Well, the idea is that for any given little x, it'll be quite rare to have a large value of this sum. So it'll be quite rare for this thing to be large. It will also be quite rare for the corresponding bit of the sum over the numbers with all their prime factors less than capital X to be large. So the probability of both of these things being large together and sort of cancelling out will be very small. So if we can show the existence of large fluctuations of this, it's very unlikely that at the same points where this gets large, the other bit of the sum will be large and pointing the other way. Cancel out. And actually, it's pretty easy if you set up the argument properly to make that rigorous. So that's why it's okay to restrict to these numbers with a big prime factor. Just note that little x starts at capital X to the 8/7. So there's a positive proportion of terms in this sum that have a prime factor. So we shouldn't have lost too much by restricting to. And the advantage of looking at this is that the numbers less than x, which have a prime factor bigger than capital X, they only have one because they're not big enough to have two prime factors of this size. And then by multiplicativity, we can split up the sum in terms of this big prime factor, so the prime factor they have, which is bigger than capital X, f of p, and then the rest of the number. So f of m for the part that's less than x. So it will suffice to show that the corresponding statement, but for this, so it will suffice to show the existence of large fluctuations of these sums. Now, I said before that these sums of random multiplicative functions don't have roughly Gaussian distributions. This sum doesn't have a roughly Gaussian distribution either. So that's an important thing to emphasize. It's not correct to think of it as having a roughly Gaussian distribution. It has a very different looking distribution with much fatter tails. But if you look at this, so we have these independent random variables f of p, and we have these sums of f of m. And the primes that occur here are all very big, and the numbers m in these inner sums are all relatively small, because they're little x divided by these large values of p. So there isn't actually any overlap between the f of p's that occur here and the f of p's involved in these inner sums. So these coefficients f of p are independent of all these inner sums. So what that means is if you kind of freeze all the randomness coming from these inner sums, it doesn't affect the randomness in the f of p's because they're independent. So if you condition on these inner sums, then what this looks like is a sum of some independent random variables times some coefficients. And that's the kind of thing that you would expect to have a Gaussian distribution. And it does. So if you condition on this huge amount of information, so you freeze this huge amount of randomness in the inner sums, then conditionally, these sums do have Gaussian behavior, conditional Gaussian behavior. You can use a multivariate central limit theorem to do this precisely. It's not so difficult. But it's important to emphasize here, there's a huge amount of information that's being extracted out. There's a huge amount of conditioning that's being performed to make this true. So just the sum individually certainly does not have a roughly Gaussian distribution. But if you condition a lot, the conditional thing will have a roughly Gaussian distribution. So now we can try to do, now we've got to something that looks Gaussian, we can try to do again what we did for the classical reiterative logarithm by analyzing the covariance structure. But now it's not the mean and the variance and the covariance, it's the conditional mean and the conditional variance and the conditional covariance that needs to be understood. So we need to understand, once we've frozen all this stuff, what do the means and the variances and the covariances look like then? Now the means are easy because the f of p is independent of all this stuff that's been conditioned on, and they all have mean 0. So the conditional mean is still just 0, so that's good. The conditional variance is not so easy to understand, but fortunately it's something that basically already arose in the in this work, showing that these sums usually have size like this. So you can show that the conditional variance here is something like the integral of the Euler product that corresponds to the random multiplicative function. So the product over primes up to capital X that corresponds to the random multiplicative function squared over this little interval and rescaled. This isn't obvious at all, but this is something that was sort of known because of this previous work. And if you look at how this behaves, so this depends on the f of p for the small prime of p, this depends on the conditioning. But you can show that with probability tending to 1, this will be bigger than 1 over v of x squared, this slowly growing function, times root log of x. So let me note here, you need this function v of x at this step to get this probability to tend to 1. So you could show that this was greater than 1 over root log of x with some positive probability. But if you want the probability to tend to 1, which we need for the overall argument, you need to put this factor in here that's tending to 1. So this is where v of x comes in the argument. And this root log of x here, well, this is a bound for the conditional variance. So if you take square roots here, you get a bound for the conditional standard deviation. If you take the square root of this, you'll get like a 1 over log x to 1 quarter. And that's the same 1 over log x to 1 quarter that's here. So in the classical case of the sums of the completely independent epsilon n's, the variance has turned out to be 1 because the typical size of the point was like square root x, just like the scaling factor. Here, the conditional variances turn out usually to be like 1 over root log x, so the conditional standard deviations turn out to be like 1 over log x to 1 quarter, because the typical size of a point is not square root x, it's like square root x divided by log x to 1 quarter. So that's where the log x to 1 quarter comes from. And now, to finish, we need to understand the covariance structure. So the conditional covariance between the sums at different points, so for little x and little y, it turns out to be something very roughly like this. So it's the same kind of integral, but with a factor x over y to the minus it inside it. So if x is equal to y, so if we're at the same point, so we're looking at the variance, then this is just 1, so it's the same thing as up there. But if x is away from y, then x over y is something that's not 1, and this will rotate as little t varies over this interval, or you might hope to get some cancellation from this factor, x over y to the minus I. And what we want is we want the conditional covariances to usually be appreciably smaller than this lower bound we have for the conditional variances. So before, when the variances were 1, we wanted the covariances to be smaller than this small number rho, let's say. So now the conditional variances are like this. So we want the conditional variances to be appreciably smaller than this if we want to get independent behavior. And you can show with quite a lot of work that with probability tending to 1 over the realizations of this random product, that will be true for a lot of pairs x, y. You can't do it for all of them, at least I don't know how to, but you can show that there'll be a lot of these points x, y if they're well spaced out, where this integral here will be a lot smaller than this, where this extra factor here gives you a lot of cancellation, and that means that this space sequence of points to x, the corresponding conditional Gaussians are behaving roughly independently. And then you can conclude the argument as before. So let me, won't really say anything about how you do this covariance calculation, which is the main sort of technical thing in the proof. It uses some kind of standard analytic number theory tricks for such things. So you look at the sum over different points of a big power of the integral that you're looking at, and you try to get some cancellation in that. You expand everything out, but actually doing it is rather delicate. So there are big contributions to these integrals from just little ranges of t, and you have to understand their structure quite well to make the argument work. So if anybody's interested, they can maybe ask about that. But to finish the talk in time, I just want to make these 2 final remarks that I promised. So I say at the start that maybe this exponent 1 quarter in theorem 1 was sharp. Why might that be? Well, in the classical log reiterated logarithm, you get size square root x times square root log of x. You get an exponent 1/2 here. Why is that? Well, that's because at a fixed point x, the typical size is like root x. And then taking the lim sup multiplies that by a factor root log of x. You look along a kind of space sequence of points. In the random multiplicative case, the typical size of a point is not root x, it's root x divided by log of x to 1/4. And the lower bound we had in the almost sure theorem in theorem 1 is again this thing multiplied by root log of x. So the relationship between the behavior at a point and the lim sup behavior is the same in the theorem in the random multiplicative case in theorem 1 as in the classical case. The answer is just different because the typical size of a point is different by this factor log of x. So this is a reason to believe that this exponent 1/4 might be sharp. It's far from being a proof of that, though. So there are a lot of issues in trying to get a matching upper bound. We don't have one at the moment. But I would cautiously guess that this exponent 1/4 is the correct thing for the partial sums of a random multiplicative function. So we also promised I'd say something non-probabilistic at the end for people who have been hanging around hoping for that. So instead of looking at the sums of a random multiplicative function, you could look at the sums of a deterministic multiplicative function like a Dirichlet character. So you could look at the partial sums of some Dirichlet character chi of n rescaled by root x. And you could ask how large this gets in some interval. So this is supposed to be an analog of the thing we had in the treatment of random multiplicative functions. So here you take a random multiplicative function, you rescale it by square root x, by the standard deviation, look at the maximum in an interval. So a kind of deterministic analog of that would be to take the partial sum of a Dirichlet character, rescale it, and look at the maximum. And in the random multiplicative case, we could say something about how large this gets with probability tending to 1. So that would be equivalent to saying something about how big this maximum gets for most Dirichlet characters. So let's say for 99% of Dirichlet characters, modulo some large. So theorem 1 would suggest, and I would believe this, that provided capital X, the length of the interval, isn't too close to the R. So let's say provided capital X is at most R to the 3/4, so that capital X to the 4/3 is at most R, then the maximum of this rescaled thing should be like log x to the 1/4 for most characters, for 99% of characters. So a lot of work has been done on partial sums of Dirichlet characters on their maximum size, but usually when we talk about the maximum, you mean the maximum over characters. So you try to find some peculiar characters where you get large values. And that's not what I'm asking here. So I'm asking what happens for most characters just by varying the endpoint of the sum. And this is a problem that I think hasn't really been studied before. So I would conjecture that this should be true. So for 99% of Dirichlet characters modulo some large prime, the sum should get as big as log x to the 1/4 times the obvious guess, the standard deviation. So the questions here are what can be proved rigorously. You should be able to get something for some range of little x just by mimicking the proof from the random case, but you certainly couldn't, by any obvious modification of that proof, do the case where little x is, let's say, r to the power 0.1. I would still expect this to be true, but there's no obvious method to attack that. Even proving something weaker than this would be interesting because, as I say, I don't think anything's really known about this problem. And also what happens for larger capital X. So when capital X starts to get closer to the conductor R, we know the answer must change. I won't go into that. Again, if people are interested, they can ask. So how does it change? What's the transition that happens when capital X gets larger and larger? Okay, so I hope some people found that question interesting, maybe, and found the rest of the talk interesting. And that's all I want to say. So thank you very much.
Thank you, Adam, for this beautiful and really clear talk. So are there questions from the audience? Yes, sir. Please go on.
Hi, okay, I'll talk. It's
Sure.
Andrew here. So I guess these last couple of slides, you're assuming that you're going to have a root log x law. It's just that kind of your floor that you're working from is root x over log x to the 1/4.
Yes.
Do you have any idea what the probability distribution is at root x over log x to the 1/4 times some function?
Yeah, so it should be a probability distribution that comes from, so use some buzzwords now. So it comes from the total mass of critical multiplicative tails. So in particular, that means that the tails are much heavier than a Gaussian. So the probability that the sum is bigger than lambda times root x log x to the 1/4 should be something like 1 over lambda squared on a big range of lambda.
Okay, and this is consistent to your conjecture of
Yeah, I mean, this is why you get the blow up this is why the moments change behavior at the second moment, because of this lambda square.
Yeah, I guess intuitively, I just think if you've got a lot of, as you say, the tail doesn't decrease very fast, then your conjectures may be risky, but you thought this through.
Yeah, so right. So it's far from obvious that this is the right answer. The main thing is that, so to get the existence of large values, you just look at the part of a sum where there's a big prime factor. You don't have to worry about the part of a sum where there isn't a big prime factor. And to get upper bounds, you do need to worry about that bit of the sum. So it's possible there could be some kind of conspiracy in that bit related to the heavy tails that would spoil the upper bound. My feeling is not, but I think until we have a proof, I don't really know. There's going to be some kind of quite subtle interaction between the tail behavior at a single point and the dependence between the sums at different points.
Yeah, thank you.
Any other questions? Okay, so if not, let's thank the speaker again. So before we end the session, let me just remind you the announcement that we made in the first session. So we are planning to upload these videos on the conference website, as long as the speakers are okay with it. So if anyone has any objections, please write to the organizers. And also, it would be nice if the speakers could send their slides to the organizers, so we could put that up as well. And thank you everyone for joining us for this session. And we will resume our third session, the final session for today, in about half an hour at 8 p.m. Indian Standard Time. Thank you very much.
8:30.
Oh, sorry, 8:30. Sorry. In an hour's time. Sorry.